Hey geometry team, and welcome to Unit 11, Day 6. We are getting through our unit here and moving along. We are going to be talking today about dilation. So a dilation is either an enlargement or a reduction of a figure. So we're making things bigger or smaller with respect to a fixed point called the center of dilation. Okay, and so it's basically you have a center point and then you look at your image and then make it bigger or smaller going out from that point. For us, we are going to stick with all of our center of dilations being at the origin and our enlargements or reductions going out from there. So you don't need to worry about what that's going to mean for anything else. We're going to stick with our dilations, just doing one thing. So you don't need to worry about your center of dilation too much. A dilation is an example of a non-rigid motion. Okay, so it's a movement that's not rigid. Rigid would mean that the shape stayed the same. But since it is going to get bigger or smaller, it's non-rigid motion. It moves, but it changes. Okay? And what's going to happen is a dilation is going to produce a figure that has all the same angles, but is a different size than before. And oh yeah, we just did that. Those are similar figures. Funny how those all ended up together in the same unit. So if you dilate something, you make it bigger or smaller, but it is still similar. So all the angles are congruent and all the corresponding sides are going to be proportional, just like we've been doing this whole unit. Which means, guess what, guys? We're going to be doing lots of proportions and lots of multiplying and dividing. You're very excited. And so our scale factor is going to indicate how much our figure is going to grow or shrink, how much it will enlarge or how much it will reduce. And we've talked about scale factor before, being the number you multiply by. Okay, and the letter we use when we're talking about scale factor is the letter K. And so if we multiply by something that's bigger than 1, our dilation, our image is going to get bigger, and so the dilation is called an enlargement. But if we multiply by something that's less than 1, but still a positive number, so think something like 1/2 or 2/5 or something like that, then the dilation is going to be a reduction. Because if you cut something in half, it gets smaller. Ooh, we're very impressed. Okay, and so what we talk about is the original picture or the original image that you have is actually going to be called your pre-image, because it's what it looked like before you changed it. And then when you have your new figure after you dilate it, that is going to be your image. And so if I'm taking a picture of you, the original, are the pre-image, and the picture I take of you is an image of you. Okay? And so if P is a point, and it's a pre-image of some point on your graph. So, look, we're going to do stuff on graphs. And so if P is a point, and then its image after the dilation is going to be called P prime. Okay, and so it's just a little, almost like a little apostrophe or a little tag up above your P. It is not a number. It's just a little, almost like a comma or something up there. And that's called P prime. That's going to go up there. And so P prime will be the image. And the scale factor is going to take whatever point you had. So if P was at XY, my scale factor is always going to multiply both of these numbers by your scale factor. So if I multiply it by the scale factor of K, X will become KX, and Y will become KY. So each of those letters becomes as much bigger as the scale factor says. All right? And so let's do an example or two of these so you can kind of see it in action. So I'm going to have triangle RST. and its vertices are at these 3 points. And so I'm going to graph those real quick. Vertex R is at -5, 1. 1, 2, 3, 4, 5, and 1. So there's R. And that was purple. And so point S, that pre-image, is going to be at -3, 1, 2, 3, 4. That's S. And then T is going to be at 2, -1. So that's my original figure. I've got RST, and I'm going to go ahead and connect it because it is a triangle, and these are just the vertices. So I'm going to connect those points, and there's my triangle. That is my pre-image. My image is going to be attained after a dilation with a scale factor of 2. So that means all of these numbers are going to get times by 2. So R prime is going to take my point R and double everything. So -5 times 2 will be -10. And 1 times 2 will be 2. So the image of R is going to be at -10, 2. So I'm going to take R here and go out to -10, 2. And that is my R prime. Then S prime is going to take the values of S and multiply them by 2. So -3 times 2 will be -6, and 4 times 2 will be 8. So the image of S is at -6, 1, 2, 3, 4, 5, 6, 8. And that's going to be called S prime. Then T is going to be at the point twice as far as 2, -1. So I'm going to take 2 times 2 and get 4, and -1 times 2 and get -2. So T prime is going to be at 4, -2. And now I'm going to go ahead and connect those. And I'm going to use a different color just to make it easier to spot. So S prime to R prime to T prime. So there is my image. That is my dilation of triangle RST by scale factor 2. Okay, let's try rectangle ABCD. So for ABCD, I'm going to have A is at -3, 0. B is at 1, 2. C is at 2, 0. And D is at -2, -2. So there's my original rectangle. And since it's a rectangle, I better connect all these dots. All right, so there's my original pre-image. My scale factor is K equals 3. So A prime is going to take A and triple everything. So I'll have -9, 0. And so I'm going to do my image in a different color. Let's go with this nice orange. So A will be at -9, 0, A prime. B prime will be at 3 and 6 because I will triple the 1 and the 2. So B prime will be at 1, 2, 3, 1, 2, 3, 4, 5, 6. C prime, I will take everything here and times it by 3. So it should be at 6, 0, 1, 2, 3, 4, 5, 6. And D prime should be at -6, -6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's D prime. And so now the image after my dilation is over here. And let's ask ourselves, does that make any sense of what we had to do? My scale factor was bigger than 1. And so did I enlarge my rectangle from little to big? And yes, I did. And so I think I probably did it right. It even still looks the same. It looks like I have my right angles. Everything is still all parallel. And so it should look similar to your original shape. Okay? Practicing along now. I'm not going to do this with every single one of them, but let's do a couple more. Let's try one with a scale factor that's less than 1 now. So here my scale factor is 1/2. So I'm going to expect that my image of this rhombus, JKLM, is going to be smaller because everything is going to be half as big. So let's see if that works. J is at negative 10, 2. K is at negative 2, 8. L is at 6, 2. And M is at negative 2, negative 4. So there's JKLM. Should be a rhombus. Let's see if it looks like a rhombus here. That's looking pretty rhombusy to me. Cool. Now let's find the image of this. So J prime should be negative 10 times a half, and then 2 times a half to get J prime. So I go, okay, negative 10 times a half would be negative 5. And 2 times a half is 1. I don't know where my brain went on that. It just did not want to tell me my numbers. Okay, and then K prime is going to take negative 2 times a half, which would be negative 1, and 8 times a half, which is 4. L prime will be 6 times a half, which is 3, 2 times a half, which is 1. And then M prime will be negative 2 times a half, negative 1, and negative 4 times a half, which is negative 2. So now I've got all my image points. Let's graph them. I've got negative 1, 2, 3, 4, 5, 1 for J prime. I've got negative 1, 1, 2, 3, 4 for K prime. And look, see, they still are in relatively the same positions. L prime should be at 1, 2, 3, 1. And M prime is at negative 1, negative 2. And oh yes, that definitely does look smaller than what I had before. I expected it to be smaller, and it looks like we are living up to expectations. So good job, team. One more. Let's try this square. Okay? Because, I mean, if you can do it with one thing, you can do it at all things. So here, for my square, I have 1 at 0, 0. That's D. I have E at 2, 4. F at 6, 2. 1, 2. Oops, this was not at 2, 4. Yeah, that's 2, 4. 1, 2, 3, 4, 5, 6, 2. And then 1, 2, 3, 4, negative 2. So there it is, D, E, F, and G. And oh, look at me getting all excited. I didn't even bother with my straight edge. Now my scale factor is 5/2. And so strange things could happen. So let's see, if I take 0, 0 and multiply it by anything, D prime is still going to be 0, 0. It's not going to change at all. Now if I take 2, 4 and multiply it by a scale factor of 5/2, 2 times 5/2 will be my x coordinate, and then 4 times 5/2 will be my y coordinate. So I'm going to have to know how to multiply fractions here. But I know that I can multiply straight across the top and straight across the bottom, and oh look, those 2's will cancel and I end up with just the number 5. In here, the 4 divided by 2 gives me 2 times 5 is 10. And of course, you can always use your calculator to figure those out if you can't do the fraction reducing in your head. For the next one, I have 6/2 times the scale factor of 5 over 2. So I have 6 times 5/2 for my x coordinate and 2 times 5/2 for my y coordinate. And so here, 6 times 5 is 30, divided by 2 is 15. Here, 2 times 5 is 10, divided by 2 is 5. And then the last one, I have 4, and there's my scale factor, and negative 2 with my scale factor. And again, I'm going to multiply straight across. 4 times 5 is 20, divided by 2 is 10. Negative 2 times 5 is negative 10, divided by 2 is negative 5. And so now I've got my image numbers. So I'm going to be up at 5, 10, 1, 2, 3, 4, 5, 10, 0, 0, 15, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, it's all the way over here. and then 10, negative 5. And there. So now I've got a shape that looks something like this. And you'll notice that since one of my points was on the origin, that some of my lines went along a straight line path together because it dilated out from there. Okay? For these last two, I didn't give you the points. I just tell you the scale factor, so you're going to have to use your brain sometimes to figure out where the points are. So here, m is at -1, 3. And you're going to have to figure that out yourself so that then you can find m prime. Now, my scale factor is 2, so I'm going to double everything here. So I'd be at -2, 6 for my m prime thing. And so to do these ones, you're going to have to figure out your original points so that you can find out your image points. All righty. Moving along from here, we got more of the same thing. So you're going to have to name your points and then use your scale factors. I'm not going to show you every single one of those. Instead, we're going to come down here where I don't even have a picture to look at, and I get to figure out everything anyway. And so notice what I have here. I said A prime is 10, -8 is the image of A after a dilation with a scale factor of 2. So notice I don't know what A was, but I used a scale factor of 2 to get A prime being -10, -8. And so I'm going to have to think, what did I double to get -10 for X? And what did I double to get -8 for Y? And that's just straightforward algebra there. You can figure out if you want to. I tend to work backward. If I had to times by 2 to get -10, to go backwards, I'm going to have to take -10 and divide by 2 to get my original number being -5. And then if I did y times 2 to get -8, I'm going to have to take -8 divided by 2 to get -4 for the coordinates of A. And so the main thing here is to keep straight which direction you're going from your image or your pre-image to your image. So here I have P prime, so that's my after value is -2, 5. So that's the image of P after a dilation with a scale factor of 1/3. So I did K is 1/3. So I times by 1/3 to get here. And so I need to find my original point. So let's think about it. If I did X times 1/3 to get -2, I can work backwards to figure out what X was. And so to do this, I'm going to times both sides by 3, and X was originally -6. And then for my Y, if I took Y and times it by 1/3, it gives me 5. So a third of something gives me 5. So if I times by 3 here, Y gives me 15. So my original pre-image was -6, 15. For the next one, for Z, I've got Z prime. So my image was 3, 8. And I got here by taking original point Z and dilating it by a scale factor of 3/2. So I timesed by 3/2. Okay, that was my K. So if I timesed by 3/2 with my X and Y to get this, I'm going to want to set up that equation. So I did my X, I timesed it by 3/2, and I got 3. So to find my X now, let's see, I had a divided by 2, so I'm going to times 2. And I had X times 3, so I'm going to divide by 3. So notice I really just multiplied by the reciprocal on both sides. Those will cancel out, and X is going to end up equaling 2. So my original X value was 2. Then for my Y, same thing. I'm going to take my Y times my scale factor. So y times the 3/2 gives me my y over here. And then I'm going to work backwards, so I'll use the reciprocal. And y ends up being 8 times 2 is 16/3. And so it doesn't have to be complicated. If you can do it in your head, well, great, do it in your head. But when we start getting into fractional scale factors, you're going to want to be more careful and maybe do some of the algebra to figure them out. And then for a really good time, what if I don't tell you the scale factor and you just get to try and figure it out? How are you going to do that? Well, my recommendation is look for your original point, your pre-image, and then find where it went. So here, let's see, let's start with D. You can use any point you want because the scale factor is the same everywhere. I'm going to just go with D because why not? So D is at the point, let's see, this is at 0, 1, 2, 3, 4, 5, 6. So it's at the point 0, 6. Then its image, D prime, is at 0, 2. And what I'm going to do is I'm going to pick any pair of those and I'm going to figure out what changed. And so to get from my original down to my image, I had to divide by 3. And so my scale factor is going to be, dividing by 3 is going to be multiplying by 1/3. So my scale factor is 1/3. This would have worked if I used point E and E prime or point F and F prime. Let's try another. Here, my originals now are the smaller ones. So let's pick point Y. So point Y is at 1, -2. Is it? Yeah, there's center 1, -2. Yep, okay. Just making sure I'm counting right. Don't want to mess everything up. So I'm at 1, -2. And my Y prime, 1, 2, 3, 4, 1, 2, 3, 4, and -10. Okay, so let's figure out my scale factor. What did I do to get from one of these to one of these? And I did that wrong. 1, 2, 3, 4, 5, 6. Oh, yep, it was -8. I assumed instead of actually counting, and I should know better, but, you know, I took a shortcut and I paid the price. That one's at -8. So 4, -8. This one's at 1, -2. So now I can see, to get from 1 to 4, I times 4. To get from -2 to 8, I times 4. So my scale factor is 4 that I multiplied by for everything. Okay, so that's what we're doing with dilations and scale factor. Then for a little change of pace, let's go back to when you were young. And let's talk about symmetry. Okay? And so once we start getting into things like dilations, it makes you start thinking about how things look. And so we're going to talk a little bit about symmetry on today as well. So we've got 3 types of symmetry we're going to focus on. We've got line symmetry, point symmetry, and rotational symmetry. Okay? Now, line symmetry is the figure can be mapped onto itself by a reflection in a line, so that if you drew a line somewhere on here, would the points on this side map directly across the line to the points on the other side. So, for example, this appears to be a line of symmetry. So everything on this side is exactly the same distance across as everything on the other side. And so it's kind of like the left is a mirror image of the right. Of course, lines of symmetry can be horizontal, or lines of symmetry can be diagonal. It doesn't matter, as long as everything on one side of the line maps directly across to everything on the other side of the line. And there can be more than one line of symmetry. So for example, down here, this is a hexagon. It has many lines of symmetry. I could draw a line of symmetry here. I could draw a line of symmetry here. I could draw a line of symmetry here. Oh, but wait, we're not done. I could draw a line of symmetry here. I could draw a line of symmetry here. or I could draw a line of symmetry here. So yes, it does indeed have line symmetry for sure. Now, point symmetry is symmetry it's a kind of rotational symmetry. So I'm going to skip point symmetry for a minute and come down to rotational symmetry. Rotational symmetry is what happens if you can take the figure and move any point on it around a circle less than 360 degrees and have it map onto itself. So if I were to turn the figure less than a full circle, because anything, if you rotate it full circle, comes back to itself. So anything that you can rotate can be rotational symmetry. And so one thing that we can do for that is to use a visual paper. So I'm going to get a piece of visual paper here to show you. Okay, so here we go. So this is kind of see-through paper, and it allows us to check for symmetry. So what you do is, if you want to check for symmetry, got to find the side I can write on. Here we go. Is I'm going to pick any point on it, and I'm going to rotate until it matches up without going all the way around. Oh, look, I rotated it. I mapped back onto my figure, but I have not gone all the way around the circle. So this has rotational symmetry. All right? Point symmetry is a special kind of rotational symmetry. This is rotational symmetry 180 degrees. And remember, 180 degrees is half a circle. So if you can rotate something halfway around the circle and it matches up with itself, that's going to be point symmetry. And again, it's just a special kind of rotational symmetry. So on here, if I take this letter N, I'm going to just kind of trace it out, okay? And I start to rotate it. It's not matching up, and it's not matching up, and it's not matching up. And so here I am 90 degrees around the circle, and it still doesn't match. But if I rotate it, so I started here, so that was up. If I rotate it so I'm halfway around the circle and now it's pointed down, now I match back up to where I was. And so since I had rotational 180 degrees, that is called point symmetry. And so on here, I have rotational symmetry, and if I take this, and here I am pointing to the top, if I rotate it and point it directly down, oh look, it still matches up. Oh, that wasn't even in camera. Mrs. Cerna, get a grip. Let's try that again. So if I start a point on the top, if I rotate it 180 degrees and it goes down, then I know I have point symmetry. And yes, an object can have point symmetry and rotational symmetry at the same time, or it might just have rotational without having point. But you can't have point unless you also have rotation. So there you have that. So let's look at this triangle then. And so trying to draw on this paper, I got to make sure I have the side that lets me draw on it. So here's my original image. First of all, can I draw a line on it somewhere that lets me fold it in half? Well, let me try that one. If I fold it in half on that line, oh look, that side lined up and that side lined up. So yep, it definitely does have line symmetry. So yes, for line symmetry, right there. Didn't have to draw it, but I felt like drawing it anyway. I could also have a line of symmetry here or a line of symmetry there. So this one had 3 lines of symmetry. Now let's check for rotational symmetry. So here's my top. I'm going to rotate it, and oh, I did rotate and match up somewhere, so yes, I have rotational symmetry. So now I'm going to check for point symmetry. So I'm going to rotate 180 degrees. So remember, I was originally pointing up. So when I try pointing down, oh, I don't match up here. And so it does not have point symmetry. It only has rotational symmetry. Trying here, this lovely parallelogram. Let's trace you out. And some of you can see this without drawing, and that's totally fine. And ooh, this purple just does not want to draw on my patty paper. Let's try this nice dark blue then. It draws nice, okay? So first of all, does it have line symmetry? Well, it might be tempting to think, well, what if I drew a line here? But if I fold along that line, you'll notice that the points on top did not map onto the points on the bottom. They're still way over here off to this side. And so it didn't reflect on itself. The points over here are coming down over here when I fold straight across on this line. And so no, this does not have line symmetry. So nope there. Does it have rotational symmetry? Well, I'm going to use a test direction and I'm going to try rotating it another. And so I'm rotating and nope, I don't line up there. Nope, I don't line up there. Ooh, I lined up here. So yes, I have rotational symmetry. Oh, and when I did it, I was straight up. Now I'm straight down. I rotated 180 degrees and matched up. So I also have point symmetry. For this triangle here, try tracing you out here. Got this right angle. Let's see, line symmetry. Well, I can't fold it this direction. What if I folded it this way? No, because that doesn't match up here. No, it doesn't look like I have line symmetry here. What about rotational symmetry? What if I rotate this? Oh, nope, 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 nope. Doesn't look like I have rotational symmetry. Well, if I don't have rotation, then I don't have point, because you have to rotate to get point. And so you're going to see how this works. I highly recommend that if you don't have some kind of tracing paper you can use, like wax paper works really good or something, even just a thin sheet of paper, if you can't tell a symmetry, just even a thin sheet of paper you can lay down or something you can mark to test is very useful. It's not required, but it is useful to just determine line, point, or rotational symmetry. Usually you're going to be able to eyeball pretty quick. Oh, yep, those have line symmetry. Oh, but this one, if I draw a line, nope, this doesn't, it's supposed to reflect straight across. Nope. Nope, so it doesn't look like line symmetry here. So you should be able to tell pretty quick if something has line symmetry. Rotation may require a little more work or maybe some tracing paper. And so looking back on here now, we purposely put some interesting different designs here so you can test rotational symmetry or point symmetry. And so I'm just going to try a couple for fun. The letter R, no line symmetry here. Rotational symmetry, I'm just going to trace down the middle here. Rotating, rotating, nope, 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 nope. That doesn't have any kind of symmetry at all. Too bad. What about the queen? Well, let's see. My queen of cards here, it looks like a rectangle. I have my Q here and my Q here. So if I rotate it 90, nope. Oh, look, if I rotate it, my Q's are still pointed the right direction. So this had rotational symmetry and it had point symmetry. But look at this. If I draw a line here, this heart wants to go right here, but there's not a heart that it maps onto. And this heart would want to come here, and there's not a heart it maps onto. Remember, with line symmetry, things need to fold across and have a match. If I try this Q doesn't have a match, and this Q doesn't have a match. So it doesn't have line symmetry. It only has rotational and point symmetry. So these are fun to kind of do and decide, what do you think is going to be the different kinds of symmetry here? All right, team, so we've talked about our symmetries, we've talked about scale factor and dilations. Go forth in geometry, and we'll see you next time.